I did a bachelor in electrical engineering, as Alistair said, and I also did a bachelor in physiology, and then went on to do a PhD in pediatrics. So a lot of the things that I'll talk to you about come from the context of pediatrics. I'm no longer in pediatric research, but it's still, there's a lot of things in there that's still relevant to research in general. So what I like to talk about is primarily where engineers fit in respiratory medicine, and perhaps you could extend it to medicine in general as well. But with regards to respiratory medicine, I'll talk about examples in which this occurs, and I'll talk about it in the context of measuring flows and volumes, which are really the bread and butter of respiratory medicine. I'll talk about respiratory impedance, and you'll find out what that is in a sec. Ventilation heterogeneity, and more recently, work which I've become involved in much more recently, which is time series analyses of lung function. So I guess you're probably, a lot of us are very familiar with the idea of that engineers create tools and make cutting-edge technology in order to get people to be able to perform better diagnosis, better monitoring, better treatment, better surgery. And that's true to some extent, but as I've told you, that the space that I've occupied within respiratory medicine has more been the role of a scientist, and found that a lot of the engineering know-how and principles and way of thinking has come in handy. And so not only are engineers involved in provision of instrumentation and tools, they're also useful in modeling and analysis of data, and contribute to a better understanding of how lung structure looks like, and how the lung functions. So basic science, if you think about it. So before I go into all that, I'll do a crash course on anatomy. Probably you've already done this as a part of, I don't know if any of you, if you've done this as part of your course, but well, everyone knows what the lungs do, I hope. They are basically an organ of gas exchange. Your body and all the cells of your body needs oxygen, and they need to excrete carbon dioxide, and the lungs is the pump, if you like, that gets this to work. So they are anatomically, you can think of it as starting from the larynx onwards, where your voice box is, and then coming down into the trachea, which then bifurcates into bronchi, which then branch into secondary bronchi, into tertiary bronchi, and it just keeps branching on until you reach, and these are basically called collectively called the airways, and they are primarily responsible for the conduit of gas. And gas travels actually by convection rather than conduction, but that's splitting hairs. And at some point they reach a point where they've branched out to something called respiratory bronchioles, and that's where the walls of the lungs are the walls of the airways are the thinnest, and they end up in these structures called alveoli, where the walls are so thin that that's where gas exchange takes place. Oxygen diffuses across the membrane of the alveoli into the blood capillaries that are surrounding the alveoli, and then carbon dioxide gets put back into the lungs, and where they can travel back up the airways to go up into your nasal passages. So just for all intents and purposes, when I say airways, I'm basically referring to this network of branch airways that carry the gases. And when I say tissue, what I'm referring to is respiratory bronchioles, the alveoli, the structure of the lung, if you like, and that's important. That will become important later on when I talk about impedance. But basically, the structure and the function of the lungs can be assessed in many different ways. You can try and work out how healthy the lungs are by measuring lung flows and volumes, and that's the simplest way to think about the lungs and how they function. Because after all, when you're breathing, when you're blowing, those are flows and volumes that you can measure easily, and there are many different ways to measure them as well. But you can also think about the structure of the function of the lungs as a mechanical system. So you can measure it in terms of its mechanics, in terms of resistance, in terms of how elastic the lungs are, and obviously that contributes to how well the lungs function later on, because they will impact on the lungs and lung flows and volumes that you get. And you can also assess the health of the lungs by different ways, like for instance, you can assess ventilation, how well it takes in gases and out gases, and how efficient it is at doing so. You can also measure it in terms of diffusion, the diffusion of the gases across the membrane, in terms of oxygenation and carbon dioxide removal, but I won't focus so much on that today. And basically, different assessments are relevant to different disease, because depending on the disease that you have, different aspects of these get affected. Okay, so however, the most standard test of lung function is spirometry. And how many of you have ever done a spirometry test before? No? Look familiar? If you're active in sports or diving, for instance, you probably would have had to do a lung function test. If you've ever had surgery in hospital, you might also have had to do a lung function test. And as I said, the most standard form of measuring lung function is spirometry. And what that does is, what that involves is basically you are asked to take a huge breath in, as much as you can, basically until you reach the top capacity of your lungs, and then you're asked to blow as hard and fast as you can. And as you can see, it's a very simple simple maneuver, and what people get, the absolute gold standard for measuring how healthy your lungs are, is the forced expiratory volume in 1 second, or the FEV1. That's how much volume can you breathe out within a period of 1 second. Another measure is the forced vital capacity, which is how much volume can you get in total out of the entire maneuver. And that's a measure of how, they're both measures of how big your lungs are. And there's often another parameter which is measured, which is another variable that's measured, which is the peak expiratory flow, the PEF, and that's simply how fast can you get to? What's the highest flow that you can get to in that maneuver? So in spirometry, you often find that you sit in a box like this, and then there's a mouthpiece that you breathe into in order to do this maneuver, and the pressures and the volumes, or specifically the flow, is measured in order to gain all these things. Volume is obtained by integrating flow. Another test that's commonly done but less commonly used in spirometry is the body plethysmography, and that's the reason you sit in the box. What body plethysmography does is measure your lung volume at rest, because with spirometry all you have is a flow measurement device that's always relative, so you can blow out, but the device has no idea or telling what volume you had to start with. Does that make sense? So you can measure how much flow you've expelled, and then you can integrate that to get how much volume you've expelled, but it doesn't tell you how big your lungs are to start with, and that's the point of body plethysmography. What you do is if you're claustrophobic, you might not like this test very much, so shut the door on you, and then as you're asked to do some normal breathing, and what they do is they shut the connection of your mouthpiece to the outside world, and at that point they know what the pressure and the volume is, and you're then asked to do a series of panting maneuvers, and by the changes in the pressure, using Boyle's law, the changes in the pressure and the volume, you can work out what your initial volume is. So that's a measure of your resting lung volume at the start. By that panting maneuver, because you've got pressure and you've got flow, you can also have a measure of resistance, or how resistive your entire respiratory system is, by taking the ratio of the change in pressure over the amount of flow that's given out. Okay. So the problem, as it may already occur to some of you, is that not everyone can do these tests. So obviously babies can't do that, and very young children. If I've got a 2-year-old, she doesn't do anything I want, much less lung function. So you can imagine that it's quite hard to get young children to do that, and that's why in pediatrics this is a big consideration. But older people also, the elderly or people with very severe lung disease, they also find this maneuver quite difficult to do, particularly the spirometry. And so really a good, ideal, gold standard lung function test needs to be Well, first of all, it needs to be non-invasive. That's almost a given. It needs to be passive, so you don't need a lot of cooperation from the subject in order to be able to get your measurement. It needs to be objective, and the reason I say this is because spirometry is known and notorious for being very effort dependent. If your subject's a bit of a slacker, you're not going to get reliable data from him or her. Often in a children's hospital, we used to get young teenage girls come in, and they didn't want to, if they came in with a friend, they didn't want to be shown to be doing these maximal maneuvers because it doesn't look good. And you do run into problems like that, even though you don't expect, you shouldn't expect to. But you are working with people. So spirometry is also, it also has a training effect. The more people do, the more times people do it, the better they get at it. So that's also a problem. It's actually a problem with any lung function test, because obviously if you do it often enough, people get better at things, but spirometry is quite susceptible to this effect. And it needs to be something that you can reproduce again and again. The measurement needs to be repeatable. And then there are also, those are technical considerations. There are also physiological or clinical considerations for a lung function test. If you want to do the test in infants, usually you need to do it when they're sleeping, otherwise they get in the way. And so you need to consider things like whether you can make the measurement when they're sleeping. You need to consider at what stage of sleeping they're at. You also need to, ideally, you'd also need to have a test that measures the same thing regardless of how old or young that your subject is. So, for instance, if you have to measure you need to think about the fact that if you're measuring babies, they're going to be lying down, but if you're measuring an adult, they're going to be sitting up. What's the effect of that on your lung function test? So these things are things that we think about when we're trying to design new lung function tests to supplant spirometry. And obviously, it needs to be a meaningful indicator of disease. You can measure a very beautiful, perfect trace of something or other, but if it's not related to disease, it's not going to be very useful for you. Okay, so there are various solutions that have been proposed in research in the past. This is probably the scariest. You can get kids to do spirometry, infants to do spirometry. I've done this test. It's not something that I would like to do again on a regular basis, but you basically can get a baby to do spirometry by attaching a vest around its thorax and abdomen, or around its chest and tummy. And basically what happens is you inflate the vest, and that causes a squeeze. It's a gentle squeeze, but it is a sudden squeeze. It looks very dramatic, and I'm hoping that I can run a video, and then you can. It's probably much more descriptive if I show you. So, whoops. No. What were you saying about old school earlier, Alistair? Yeah, thanks. Okay. Hopefully this works. Should have tested this before. Okay. So usually you get the babies sedated, but there are labs who try and get the babies to sleep by giving them a good feed before, so that they're sleeping nice and deep. It's not being harmed in any way, but I know, but it does look quite dramatic, and you can see why I am not a big fan of doing this technique. But that vest here is attached to a pressurized system, and then basically what happens is this is something that I'll show you later. It's a pneumatag. It measures the flow coming out of the baby. And yes, so you inflate the vest, and it causes the squeeze, which is basically which mimics the adult maneuver that you have that tries and empties your lungs as much as you can. You won't completely empty it. You have always a certain amount of air in your lungs. It does sound like that as well. And yes, it is run by a DOS-based program. And you may laugh, it's actually used in several different centres around the world because this is the best they've got in terms of infant spirometry. No, it's so basically this is you do subject the infant to a pressure so that he or she basically does an inhalation and then passive exhalation, inhalation, exhalation, and then at some point you raise the pressure up to what should correspond to total lung capacity, and then that's when you inflate the jacket. So that it's the infant doesn't do the expiration, but physiologically, inspiration is an active process. So you inhaling is dependent on the effort that you put in on the muscles, but expiration is an entirely passive process. I'll stop that. Which means that once you get to a certain pressure, when you exhale, that's almost wholly dependent on the mechanics of your lungs rather than on a conscious effort on your part. And so with that, it is somewhat different lying down or standing up. And so you obviously can't study infants standing up. So that's something you need to always take into account when you are extrapolating data from infant to adults. The other thing that with infant spirometry is that 1 second, the FEV1 is irrelevant for an infant because they empty their lungs within much sooner than that. And so so in order to take that into account, they scale that back and make it FEV1 0.5 or FEV1 0.75. So it's a very crude way of looking at things, but like it or not, the infant spirometry actually is one of the most sensitive tests around, even though it's very labor intensive. It requires great technical expertise on the part of the operator. It needs sedation, which is also not a great, not an ideal lung function test. It's quite daunting to parents, but it is one of the more sensitive measures that's related to disease. Okay, so other things you look at with infants or young children, there are people who think, okay, maybe we can just look at tidal breathing. And by tidal breathing, I mean just normal breathing. There's got to be some information found in there. And actually, pediatricians do look at normal breathing traces and plot. They plot volume versus time. They plot flow versus time. They also plot flow versus volume. And if you like, it's like a state phase-space diagram. But that from these loops that you form by plotting the flow versus volume, you can actually you can make certain inferences about the infant's breathing pattern and even obstruction and restriction to the respiratory system. But it's all been very empirical. It's all been subjected to eyeballing. So basically, the clinician looks at the trace and says, okay, this pattern looks, I mean, I won't go into the details of it, but no one has, I mean, there's been some attempts to try and quantify what the clinicians are seeing, but nothing has really made it to the mainstream. It's really still very much a research area. So that's tidal breathing. So I've talked about these two things, but before I go any further, I'll just talk about flows and volumes because this is a class on bioelectronic design. I imagine you must be interested in what how you actually go about measuring the flows and volumes. Well, the gold standard for measuring flows in respiratory labs is the pneumatachometer, which essentially is just a flow resistor. So you can implement, you can have a flow resistor in different ways. In a flash pneumatac, you've got a series of very thin capillary tubes set together, and that basically forms your resistor to the flow. And in a Lilly type pneumatac, you have a metal mesh that forms the resistance to the flow. And how you measure flow is you've got, you basically measure the pressure drop across that resistor. So if you, for the electrical engineers in you, you can think about this as being analogous to voltage and current. So pressure is voltage. The presence of a pressure difference or the presence of a voltage difference causes a current or causes a flow, and that is introduced there by that resistor. So what you do is you have a differential transducer, and either ends of the differential transducer measure the two ends of the pneumatic resistor. So this remains today the most commonly used, most well-validated method of measuring flow in respiratory physiology. I say well-validated, and what I mean by that is that labs have used it, measured its variability over days, over months, measured its linearity characteristics are the most understood. So it needs to, when you come up with new technology, it needs to go through that entire process before people will actually even think about trying it out on a larger scale. Another way to measure flow is maybe something that you may have come across if you're familiar with sleep studies, which I'll also talk about briefly later, and that's called inductance plethysmography. And what that is basically, they're basically strips that you wear around the chest and around the abdomen, and they're basically strips of wires, and you sit them in something that reads a magnetic field, and the movement of the chest and the abdomen causes generates electricity in the coils of wire that you have. So electromagnetic induction, and therefore that translates into electrical signal that's proportional to the movement, and that's your flow measurement. It's good enough for a lot of applications, but again, it's not the gold standard. It's not a very accurate measure of flow, because the effort that you exert or put into breathing often doesn't translate to an actual flow at the mouth, and so it's you need to always so measurements made by pneumatic will not correspond always to measurements made by volume displacement or inductance plethysmography. This is a method that's increasingly used. It's an ultrasonic flow meter. I don't know if you're familiar with this one as well. It's been used in a couple of commercial systems now in pediatric applications, because it's capable of measuring very small flows, which is a problem with the pneumatic. It's problematic. It's not very sensitive to very small flows. It's obviously dependent on how big and the configuration of the pneumatic is. But with an ultrasonic flow meter, what you do is basically you have a piezoelectronic transducer on this end and this end. They're at an angle to the direction of flow. You transmit a ultrasonic pulse this way and that way, and the delay so the presence of flow will cause a delay or an acceleration in the pulse being transmitted, and that will be proportional to the flow that you have. And it's a very accurate way of measuring flow in very young subjects, very small subjects. Okay. So that brings me to respiratory impedance. I'll talk about respiratory impedance first, and then we'll maybe have a break after that. Okay. How are people going? I was saying to Alistair, I realized this is the post-lunch lecture, so I'm imagining it. I'm hoping I don't have to introduce exercises and breathing techniques in the middle of it. But put up your hand if you're still awake. That's good. Okay. That's good. That's almost all of you. Okay, so I talked about respiratory impedance. So I've already briefly touched upon the fact that you can draw analogies between pressure and flow and voltage and current. And so that's all thinking in terms of DC, but you can actually think about, you can actually apply the concept of impedance as well to the respiratory system. And in fact, in around 1956, this guy named Du Bois, and I say Du Bois because he's American, and he calls himself Du Bois, realized that you can do that with people. So he had a plethysmograph, which I talked about earlier, body box, and I think he used an aircraft. This is anecdotal This is anecdotal, so I'm not sure whether this is true or not, but legend has it that he had an aircraft engine piston, attached it to the body box, and that allowed him to superimpose a sinusoidal mechanical wave into the system. And he found that when you vary the frequencies at which you cycle, the frequency of that input signal, if you like, you get very different relationships between pressures and flow. And so the respiratory system has a frequency dependence. And so you can imagine it opens up a whole new area of thinking, because then suddenly you can apply all these engineering methods to what you're measuring. You can also partition, so in this case then, impedance becomes the complex ratio between pressure and flow, taking into account the frequency. And so this is first year circuit analysis for you. And the advantage of that also is that you can start thinking about not just resistance, but you can start thinking about reactance as well. You can start thinking about not just the in-phase component of impedance, not just the ratio between pressure and flow that's in phase of each other. You can also think about the out-of-phase component. And this, in respiratory terms, is changes in volume. So resistance would be anything that causes, actually I'll go into that later, but there's a real, you can have a real and imaginary component to the impedance, which we'll find out later is actually meaningful. You can meaningfully apply that to bits of the lung, to lung function. And I've mentioned this also, that you can study the frequency dependence of mechanics, and that will also tell you a little bit more about the airways and the tissues as well. And I've got two diagrams here because Du Bois actually looked at applying it at the plethysmus graph, subjecting this oscillatory signal to the box, and that causes that is effectively superimposing your signal onto the body surface. But you can also superimpose it to the airway opening at the level of the mouth, via the mouthpiece. And he used a sewing machine motor in this case to deliver these oscillations. You don't need as powerful oscillations, and you can get what is basically input impedance, whereas previously, in the previous case, by superimposing, by subjecting pressure oscillations at the body surface and measuring, you always measure at the mouth, you're getting a transfer impedance. Input impedance is the most commonly used in research today, perhaps because of the ease with which you can implement it. There are other considerations as well, but I won't go into it today. So I talked about frequency response. Why is it important that you get different impedance characteristics depending on what frequency you're looking at? Well, that's because different parts of the lung have different characteristic frequencies. So if you try to measure impedance across a range of frequencies, this is roughly the graph that you will get. This is the real part of the impedance, and it's very reminiscent of an RLC circuit. You've got the real part is contributed to by any parts of the lung that have friction. It's a Newtonian resistance. So any impedance to flow due to friction, due to the gas being carried across the airways, will contribute to your resistive part of your impedance. The reactance is a sum of the inertance that you see in the airway, and this would arise out of primarily the bulk of gas, the inertia of the gas that's being oscillated inside the airways, and then to a lesser extent also the inertance of the mass of the airway walls. But primarily, particularly at the lower frequencies, what you're seeing, reactance is dominated by the elasticity of the lung. The lung is, as you can imagine, a very elastic organ. It has to expand and fill, and that's due to the characteristics of the lung tissue. And this suddenly now, reactance, you have a measure, you have a way to measure that. You have a way to measure how elastic the lungs are. The other point to make is that at low frequencies, the time constants of the tissues are very long, and therefore the frequency response of the lung tissue tend to be on the low side. So this part of the spectrum is dominated by the behavior of the elastic parts of the lung, the lung tissue. And as you get to higher and higher frequencies, it becomes more difficult, the signal becomes more and more attenuated. And so the higher frequency part of the impedance spectrum is dominated by the more proximal airways. And so you've got a convenient way to separate the airways and the tissues by looking at impedance and looking at multi-frequency, the frequency spectrum of impedance. Not a lot of people do this. In practice, for instance, where I'm working at the Woodcock now, people just look at lung measurements at a single frequency and work out impedance from that point, and there are technical considerations for doing so. But you can be more sophisticated than that and look at the spectrum. So I'll just have a couple of diversions where to do with the measurement of impedance itself. So if you recall, with the measurement of impedance, you had a pneumatic, and then you had another pressure sensor, and that allows you to get your pressures and flows. That's a very simple way to do it. But it does have a problem when you're measuring things using this technique. I should mention it's called the forced oscillation technique because you're forcing oscillations onto the respiratory system. You're dealing with oscillations that have to be very small because the lung is not a linear system, and when you're trying to measure impedance, you try and make it a linear system. And to do that, you need to introduce a very, very low amplitude oscillations. Otherwise, you will run into a nonlinear relationship between pressure and flow. So you have to make that assumptions by keeping your signal very, very small amplitude. The problem is that when you deal with especially very small subjects or very high frequencies, then you often need to measure very small flows, and the pneumatic is not very good for that. And so one configuration one way to measure impedance when you have very small flows is to use something that's become known as the wave tube technique. And all that is basically you have a tube and you know the characteristic impedance of that tube, and that's indicated by Z0 here. And I don't know if you would recognize this, but this is basically derived from transmission line theory. And you can, knowing the characteristics of that wave tube, you can measure your impedance from 2 pressure points along that wave tube and essentially measure the impedance as a load impedance at the end of that tube. And so having that very high impedance tube as part of your measurement setup makes it easier for you to be able to measure very, very small flows. So that's been around for a while. And when I was doing this as part of my PhD, and I was interested in whether, so up to that point, people had primarily been interested in the lower frequency low frequency oscillations, and I was interested in knowing whether you can get just as much information by going up to higher frequencies. But to do that, I needed to be able to measure low and high frequencies at the same time. But the problem with a wave tube is that you need to keep it a certain length in order to not introduce standing waves in the tubes. And standing waves are, if you recall, pipe organs, I guess, would be the easiest analogy. At a certain length, you start to see these, you start to see resonances and anti-resonances, and that will muck up. That will obviously introduce a very artificially high or low impedance in your system. And so you need to keep the length below the minimum that will generate that standing wave in that tube. But if you keep the tube too short, then you're going to have you're not going to have a very high impedance wave tube. And when you do that, you will risk the quality of your low frequency measurements. And so in order to circumvent that problem, you can pretty much ignore the rest of this diagram. I'm sorry about that. I couldn't find another one that's less busy. But basically, we introduced 3 transducers to the system. And so this is your wave tube for the low frequency measurement. You make, to get your low frequency impedance, you consider the wave tube to have P1 and P3 as your lateral transducers, but when you're trying to get high frequency measurements, you just take the impedance measured from your P2 and P3 transducers, and that's how you're able to get both high quality low and high frequency impedance from that. So that was a way to circumvent that. We've since found another way to do it, but I just thought that might be interesting to you or not. Once you have the spectrum, what do you do with it? So people are quite happy to just pick a point and say, okay, I'll measure it at 5 hertz, as I say, and then see how the impedance changes and how that changes with disease and how that changes from day to day. But as I said, if you look at the spectrum, you can go so much further than that, and people have. And so when Du Bois, again, came up with the method of measuring impedance, he also came up with a model for the lungs. And as you can see, it's very analogous to the electrical case. So the airways are primarily resistive. There's very little elasticity in the airways because they are essentially rigid walls. And so that's why you've got a resistor there, and you've got an inductor. The inductor is inertance. It's an analogous to the inertance that you see. So as I mentioned before, the movement of bulk gas, that contributes to the inertia, the inertial component of the impedance. There's a compliance here, or a capacitance, because as you get, and you can imagine, as you oscillate faster and faster, the lungs, the gas, the compression of, the reason signal gets attenuated is because gas compression causes because of gas compression effects in the airways. And so as frequency gets higher, effectively, this part of the respiratory system is less relevant to the impedance because, whoops, sorry. And so you effectively only have that pathway. So that, to model that, you put a capacitor there. And then the rest of the lung is basically the tissues that I was talking about. And there you've got the primary driver of that is the primary driver of the impedance at the tissue level is the capacitance, again. And that's this time you can think of it in terms of really a storage, an energy storage capacity, because it's an elastic component that expands as current goes through. And so that's the biggest contributor to the impedance, and then you will have some amount of inertance as well, and some amount